Hello, welcome to our final lecture, section 7.5, area between curves. Our last section, I think, is really perhaps the most important section we've done all semester long. For one thing, it tells us, the fundamental theorem calculus told us how to evaluate integrals in a fairly easy way. There's no Riemann sums going on, no area approximations. If you want to integrate a function, find the area under the curve, you need to find an antiderivative. Find an antiderivative and evaluate at the two endpoints, take the difference. So it told us, one, how to evaluate these integrals in a somewhat easy way. In truth, finding antiderivatives can be very difficult, but we'll brush that under the rug for now. And secondly, it relates these two concepts we've been studying all semester long. It relates integrals and differentiation together very intimately. It says they're complete inverse processes. Integrating undoes differentiation, and differentiating undoes integration. So we'll do one more topic here, one more application of areas under curves, and this is we want to look at area between curves. So I've put up two curves on the board already. We'll start off with a concrete example. I've got one function y equals x, just a straight line, this linear function, and then this upward opening parabola is just as easy as a parabola as you could hope for, y equals x squared, and I've indicated their points of intersection. Obviously this point right here, the origin, I haven't labeled it, it's x equals 0, and the other point they intersect is when x equals 1. So we're going to look at two things here. One is, what if I said, what's the area under y equals x from x equals 0 to x equals 1? So in other words, we're looking for the area under y equals x, so we're looking for the area of this shaded region, this triangular region. Well, one thing is you could compute this using just simple geometry, right? This is a triangle, the area is 1/2 the base times the height, but we know how to do integrals now. This would be the integral of the function y equals x. So integrate x dx from x equals 0 to x equals 1. And if you compute this algebraically, you're going to get antiderivative for x would be increase the power by 1, x squared over 2. So 1/2 x squared, evaluated from 0 to 1. Plugging in 1 just gives us 1/2. And we'll do this formally. This will be 1/2 times 1 squared minus 1/2 times 0 squared. That's 1/2. Right? So there's the area of the white shaded region. What if I said, what's the area under y equals x squared? Area under y equals x squared, again, from x equals 0 to x equals 1. So what's that graphically? I've got green here. That would be the area under the parabola. So this shaded region in green. Hoping the camera has enough contrast that this shows up nicely. Well, that's the integral of the function y equals x squared from 0 to 1. So that's the integral from 0 to 1 of x squared dx. Again, not a hard antiderivative to compute. That would be x cubed over 3, so 1/3 x cubed. That's evaluated from 0 to 1. And do I have enough space? I think so. That would be 1/3 times 1 cubed, plug in 1, minus 1/3 times 0 cubed. That would be 1/3. Okay, so that's not really what we want to do in this section. That's what we've been doing so far. What we want to find is the area between curves. So neither the white shade region or the green shade region, I want the area between these two curves. I want that area in red. How can we find that? And if you're thinking geometrically, you can already answer this question. To find the area in red, I could have taken the area in white, that's really hard to see now, but the area in white, the area under y equals x, if I subtract off all the green stuff, the area under y equals x cubed, I'm left with the area in red, right? So take everything in white, subtract off everything in green, and I'll have this area left over in red. So the area between y equals x and y equals x squared, well that should be, okay, so that should be the area in white. We've already computed it, but I'll write it as an integral again. It would be the integral from 0 to 1 of x dx minus the area in green, minus the integral from 0 to 1 of x squared dx. And because we're going to do this so often, you don't often write this as two separate integrals. I'm just going to combine these as one. So this will be the integral from 0 to 1 of x minus x squared dx. And if you were to work this out, you'll get that this equals, what do we have? I think we had 1/2 minus 1/3. Yeah, we had 1/2 minus 1/3, which I believe is 1/6. Not really important to us right now what the answer is. But setting up this integral that tells us the area between the curve is important. So what do? How do we get this? Well, all that's really happening is we're taking the integral of the upper function, the upper curve, the one that's further away from the x-axis, minus the lower function, the one that's closer to the x-axis, has the smaller y values. So this is the upper function, and this is the lower function. And this is how you find area between curves. You just integrate from the left-hand endpoint of the boundary on the left to the right-hand endpoint of the boundary on the right of the upper function minus the lower function. Which means you need to have a good understanding of what the region actually looks like. You need to know what your bounds of integration are going to be, and you need to know what your upper curve and lower curve are. I'll also say one more thing, is area between curves, this is always positive. It doesn't matter if it lives below the x-axis or above the x-axis, we're not doing net area or anything here. When we're computing area between curves, this is an actual geometric quantity, it's a positive area. So this is always positive. Which means if you get a negative answer, you know you've done something wrong. A very common mistake, a very common way of getting a negative answer is to get these two flipped the wrong way around. So instead of doing the upper minus the lower, you've done the lower minus the upper. The good news is if you do that, you're just off by a factor of -1. So you could take the absolute value of your answer and you'd still be correct. But we'll do some examples. So as always, we're going to ramp up the difficulty here. We're starting with a fairly easy one because I'm telling you exactly what the shape looks like. There's really no, you don't need to draw it because you already know what your upper curve is, your lower curve is, your left and right boundary curves. I've already told you in the description. But in perhaps building the habit of drawing pictures of what's going on, because it helps, I'm going to draw exactly what we have here. We have y equals x. We got this curve y equals x. Then we have y equals e to the x. What does that look like? Well, if x is 0, it's 1. So there's 1. And as x gets bigger, this function blows up very, very, very quickly. So here's y equals x. Here's y equals e to the x. And of course continues on in this direction. As I said way back early in the semester, I think the review sections, it really helps if you understand or know what the graphs of basic functions are. Because doing stuff like this helps, I think. And so we've got this function above, y equals e to the x, this function below, y equals x, and we're bounded on the left by x equals 0. There's x equals 0. And to the right by x equals 1. And my bounded region here is, of course, the region that's bounded to the sides by these two vertical lines and above and below by these two curves. there's our bounded region. And the question is to find the area of that region. Well, we just sort of talked about how you would do this. My area is going to be the integral from the left to the right, so from x equals 0 to x equals 1. That might be the best looking integral sign I've ever drawn. It's really, really nice looking one. Anyway, and what do we integrate? We integrate the upper curve minus the lower curve. Right, so we have y equals e to the x is the top curve, y equals x is the bottom curve, so we integrate e to the x minus x dx. And that's perhaps the hardest part of the problem, is setting that up. It's set up now, and now we just have to integrate it. These integrals could be hard. This could require substitution or something, but in this case it doesn't, because each piece isn't particularly bad. Integral of e to the x is e to the x. Integral of minus x is minus x squared over 2, so 1/2 x squared, and that's going to be evaluated from 0 to 1. And we'll go ahead and plug in these upper and lower bounds. Plug in 1, we're going to have e to the 1 minus 1/2 times 1 squared is minus 1/2, minus whatever we have when we plug in 0. And be careful again to put a bracket here. This should be minus everything in here, so the negative gets distributed. E to the 0, plug in 0, we've got e to the 0, which is 1, minus 1/2 times 0 is minus 0. So what are we looking at? We're looking at e minus 1/2 minus 1, that is e minus 3/2. And there's the exact answer. Again, be careful, my math lab, maybe it says give an exact answer, maybe it says approximate your answer to 3 decimal places or whatever. Be careful with your formatting there. But that really wasn't many lines of work, right? It's just 3-4 lines of work for this very strange shape. And the answer, the exact area between these two curves that's an irrational number, and yet we can find it exactly in just this little amount of work. Calculus is extremely powerful. All right, ramping up the difficulty a little bit. Here's another question. Find the area of the region bounded by the two curves, y equals 5x minus x squared, and y equals x. So I'm going to need a picture. Why? Because just looking at these two things, I don't know what my upper and lower curve are. I don't know which one's the top curve, which one's the bottom curve. Although technically it doesn't matter which order you put them in, because if you get a negative answer, you probably just flip the order and you can take the absolute value of it to be fair. But I also don't know what my left and right hand boundary points are going to be. So I need a picture of this. I need a picture of these functions. And before I can graph them, I need to know where they intersect. Because it turns out if I'm claiming that there's a bounded region between these two curves, and these two curves have to intersect at 2 different points. So where do they intersect? Well, they intersect when their y values are the same. So we'll set them equal to each other. We'll set 5x minus x squared. We'll ask when that actually equals x. It's when two curves intersect, it's when their y values are the same. And we'll try and solve for x. So let's see. Let's just put everything on the right. So this will be 0 over here is equal to plus x squared. And then minus 5x on this side will be minus 4x. I was stalling there because it's uncomfortable to me to put everything on the right. I like to have 0 on the right. But in any case, we'll just work from left to right here. 0 equals, we'll factor x times x minus 4. And that means we have 2 intersection points. X is 0, or x minus 4 is 0, so x is 4. So here's our 2 intersection points. And that alone is actually enough to graph exactly what's happening, because the other two parts of these functions are well enough understood. I have y equals x. Y equals x, straight line through the origin, slope 1. There's y equals x. Now what about this function? This is a quadratic. Usually we write the x squared term first, but it's a quadratic, so it's a parabola. And because my coefficient in front of x squared is negative, it's a downward opening parabola. So that means it must look something like this. And something like this, of course, intersects this curve y equals x in two different points. And the 2 points I know where it intersects, we already found them. It intersects right here at x equals 0. And right over here, let's say, at x equals 4. So a downward opening parabola that cuts through these 2 points, maybe it looks something like this. Not the greatest drawing in the world, but our picture has to look something like that. A downward opening parabola cutting through at 0 and 4 has to take that shape on. So the region we're looking for, the region bounded between the two curves, is all this stuff in red. Okay, so what's our area going to be? So we're going to integrate the top curve minus the bottom curve. So the top curve is the one that's further away from the x-axis, has the bigger y values, and according to this picture, that's the parabola. So our upper curve is 5x minus x squared minus the lower curve. The lower curve, y equals x minus x. And what are our bounds of integration? In the last problem we did, it was pretty easy. They just told us go from left to the right, and they gave us those curves. But here we had to solve for them. We found that actually they intersect at x equals 0 and x equals 4. So the furthest left we are is 0, and the furthest right we get is x is 4. So we're integrating from 0 to 4. And that expression, whatever that integral works out to be, that is exactly the area between these two curves. And we'll go ahead and compute this. Integral from 0 to 4, I just want to clean this up before we integrate. 5x minus x is 4x minus x squared dx. I think the integrals aren't too bad now. We're going to have 4x squared over 2 is 2x squared. Right? This becomes x squared over 2 when we integrate it. 4 over 2 is 2. Minus x cubed over 3, so minus 1/3 x cubed. And that's going from 0 to 4. Let's see, do I have enough space? I'll write small. When we plug in 4, what do we get? 2 times 4 squared, 2 times 16 is 32. Minus 1/3 times 4 cubed, 1/3 times 64 is minus 64 thirds. Minus what you get when you plug in 0. When I plug in 0, this quite often happens when you plug in 0. Not always though, you have to check. But in this case, when I plug in 0, I've just got 0 minus 0. So what is this? Well, it's 32 minus 64 thirds. I should probably write this as a single fraction. 32 is how many thirds? 96 thirds? 96 thirds minus 64 thirds. Our answer is, if I would just squeeze it in there on the bottom of the board, is 32 thirds. Is the exact area between these two curves. So we'll do one more. There's some on my math lab that are actually pretty difficult. I'll do one more, ramping up the difficulty yet again. But don't forget this process. If it's not given to you what your left and right hand boundary curves are, or boundary points are, if it just says a region bounded between two curves, then you're going to have to find the points of intersection. There's no getting around it. You have to know when your two functions intersect in order to set the bounds. How do you figure out when two functions intersect? You set them equal to each other. Alright, one more problem. Find the area enclosed by this quadratic function, so a parabolic curve, y equals x squared minus 2x, and y equals x again. And keep going with y equals x because it's an easy function to graph and generally nice to work with in these examples. But enclosed by these two curves on 0 to 4, integral from 0 to 4. Or, yeah, the interval from 0 to 4. And what I'm going to do here is I'm going to draw this. I'm going to illustrate exactly what's going on, because if you're not careful with understanding exactly what's going on in this problem, then you're not going to get the right answer. So, first things first, I think I need intersection points again. Let's figure out where these two functions intersect. So we're going to set them equal to each other. One is x squared minus 2x equal x. Well, subtract x from both sides. That means x squared minus 2x is equal to, or sorry, minus 3x is equal to 0. That means x times x minus 3 equals 0. So we have two intersection points. X equals 0. Or x minus 3 is 0, so x is positive 3. So let's attempt to graph this. Y equals x, no problem. Straight line through the origin. What about this other curve? Again, quadratic function, so it's a parabola. Coefficient in front of x squared is positive. It's an upward opening parabola. And it cuts through this curve at 0. X equals 0. And x equals 3. Okay, so parabola cutting through those 2 points. I'm going to have to draw this fairly steep to make it look reasonable. But something, I missed my point there. I'll move it over. Okay. So what's the area, or what's the region we're looking for? Well, we want the area enclosed by these two curves, but we don't want it from 0 to 3. You might be thinking, I want to find this area here. That's normal. If I just said find the area between the two curves, that's what we'd be looking for, 0 to 3. But this actually says find the area enclosed by these two curves on 0 to 4. So let's say this is 4 right there. The area enclosed by these two curves from 0 to 4 is the area between them from 0 to 4. So it is in fact this area, but also that area in red. Okay. So I know I want to integrate from 0 to 4, but what's my upper function, what's my lower function? Well, if I go from 0 to 3, y equals x is my upper function, and then the parabola, y equals x squared minus 2x is the lower function. But once I pass 3, from 3 to 4, they switch. From 3 to 4, the parabola is the upper curve, and y equals x is the lower curve. What this means is I have to treat these two areas separately. I need to find this region in white and this region in red separately, and then add them together, because the area between the curves is given by different expressions. In this case, it's x minus this parabola, and in this case, it's the parabola minus x. And I have to do this. Otherwise, I'm going to get the wrong answer. So my area, this is sort of like the example we did at the very end of last class, is how about I give these two regions names. This region would be R1, and this region would be R2. So the area is R1 plus R2. Finding R1 is no problem. It's the integral from 0 to 3 upper function, y equals x, minus the lower function, x minus 2x, x squared minus 2x, sorry. Again, be careful, put that all in parentheses so the negative distributes over the whole thing. Dx plus R2, so integral from 3 to 4. 3 to 4. Now I have a different upper function. Now it's the parabola x squared minus 2x minus x dx. This is why I had to break them up, right? These two integrands are different. In one case I've got x minus x squared minus 2x, and over here I've got x squared minus 2x minus x. So very different integrals. And I'm going to erase my picture now because I need space to do these things. But if we bring this all the way over here, I'm still not sure that's enough space. Bring this all the way over here. This will be, let's simplify this a little bit before we integrate. 0 to 3, x minus x squared minus 2x, that's x plus 2x is 3x. 3x minus x squared dx plus integral from 3 to 4 of x squared minus 2x minus x minus 3x dx. I don't think these integrals are particularly hard. This becomes 3x squared over 2, so 3 halves x squared minus 1/3 x cubed. That's going to go from 0 to 3 plus this integral 1/3 x cubed. And all I'm doing here is raise the power by 1, then divide by the new power, minus 3x squared over 2. So minus 3 halves x squared from 3 to 4. So you plug in these values, we've got 3 times 9 over 2 is 27 over 2, minus 27 over 3 is minus 9, minus plug in 0, you just have minus 0, plus, now we plug in 4 cubed over 3, 64 over 3, plus 3 halves times 16, so that's 16 over 2 is 8, 3 times 8 is 32, no, 3 times 8 is 24, minus whatever you get when you plug in 3, that's interesting, minus when you plug in 3, we're going to have 27 over 3 is 9, and minus 27, 3 times 9, 27 over 2. Lots of fractions here. These don't cancel. This is minus 9, so that's minus 18. But I've done the work. This eventually simplifies to, if you want to check, 19/3. So quite a complicated example. It didn't look like it was going to be that complicated right off the bat. If it just said find the area enclosed by those two curves, no problem, right? We would have just ended up with this piece, because the area between the two curves, strictly between the two curves, enclosed by the two curves, was from 0 to 3, but it made it harder by saying actually go from 0 to 4. Which meant we had to add on this extra piece, the region from 3 to 4. And in seeing that, in order to see that, we had to really have a good understanding of what the graphs even look like. We had to understand the graph before we could do any of that. Sometimes my math lab will give you a picture of the curves, but I won't guarantee it, not always. So be careful. All right, so now that we have under our belts the ability to find area between curves, we're going to end with discussing this concept of economic surplus, which is going to be defined in terms of specific regions between curves. So what I've drawn up behind me here is just a standard supply curve for a good and a demand curve for a good. So my demand curve is given by P is D of Q, D for demand. The supply curve is P is S of Q. And that means my independent variable here is Q, which is quantity, and P is the price. So what's the market price? Well, the market price, of course, is, if you know anything about economics at all, you know that's when supply equals demand. So this point right here, this value, the price over here, that I'll call P naught, that's going to be the market price. Or sometimes called the equilibrium price. Okay, and the point where it happens down here, in terms of quantity, this will be Q naught, and this is our equilibrium demand. Equilibrium demand. And by the way, this point right here where we actually have equilibrium with supply equaling demand, I'll just label that as equilibrium. Okay, so we're talking about economic surplus here. I want to talk about two separate concepts. Let's say, suppose I choose a value less than Q naught. Suppose I come in here and maybe I choose like 2 people. Alright, so I look at this and I look at this and I see, okay, those 2 people, this would be S of 2. Those 2 people are willing, oh sorry, I'm on my demand curve here, my bad. That's D of 2. Those 2 people are willing to pay this much. And this price they're willing to pay is more than the actual market price. It's more than the equilibrium price. Right? So these 2 people are willing to pay more than they actually did, because this is the market price right here. Then I come over here to maybe 3 people. These 3 people aren't willing to pay as much as those 2, but they're still willing to pay more than the market price. How much more? Well, that much more. Similarly over here, this much more. Well, what if I do this for everybody? What if I work out how much more all these people were willing to pay than they actually did? Well, I'm looking for that area then. I'm looking for that area. All those people essentially saved money. Right? They saved money because the market price was set to a price less than they were willing to pay. And all the money that they saved in total is represented by this area, and that area is what we call the consumer surplus. So, how would I give it a different color? Let's go in red. And I'll do this all in red. Alright, so that area, that's called the I think our textbook puts an S on the end, some people don't, I'll just call it the consumer surplus. And what's it equal? Well, it's the area between these 2 curves. So what's my upper curve? I'm integrating something. My upper curve is the demand curve, so D of Q. What's my lower curve? Well, my lower curve is just this white dotted line here. What curve is that? Well, that curve is P naught. So it's D of Q minus P equals P naught. P naught being the market price. dq. What are my bounds of integration? I'm going all the way from the left, Q equals 0, to the equilibrium demand, Q naught. So 0 to Q naught. And this is our definition. Hopefully the red is showing up well on the camera. It's the integral from 0 to Q of the demand function minus the market price. Let's do the same exercise, but down here. Again, go to 2. 2 people. This is the supply curve. So this value right here, S of 2. There's 2 people willing to sell this good for much less than they eventually sell it for, because they're willing to sell it for way less than the market price actually is. So all these people, these 2 people, they made money. They made more than they intended to make because they're willing to sell it for way cheaper than market price. How much more money do they make? Well, this distance right here. The distance between the price they're willing to sell it at and the price they actually sold it at. Coming to 3, same thing. So same story. All of this area in green, this represents the so-called producer surplus. The extra amount that the producers have sort of made by selling at the market price rather than the price they were willing to sell at. So the area over here in green, oops, why did I stop my arrow there? This area, that's called the producer surplus. And what's this going to be? Well, once again, our bounds are the same, right? It's from 0 on the left to the equilibrium demand, Q naught. 0 to Q naught. Of the upper function, so the upper is the market price, right? The upper curve here, bounding the top of this region, is P equals P naught. So it'll be P naught minus the lower curve, the supply curve, S of Q. Integrated with respect to Q. And there's our 2 formulas. So you're going to have to commit these to memory, but this is the formula for consumer surplus, this is the formula for producer surplus. In truth, if you understand sort of what they represent in terms of area between 2 curves, then you don't really have to memorize, right? You can sort of derive those things every time if you just realize, oh, I'm finding the area between the market price and either the demand curve or the supply curve. Let me check the camera, make sure you can actually see these. Yeah, they look readable. Okay, so we'll do an example. Alright, so I think we only have time for one example here. I'll do one where we sort of have to go through the whole process. You'll see other examples where maybe quite often what happens is you're only given one of these curves, supply or demand, and then they tell you the equilibrium point, and that's enough for the problem they're posing. But in this problem, I'm saying, okay, suppose the supply function for oil is given by this function, S of Q is Q squared plus 10Q. And the demand function is given by d of q is 900 minus 20q minus q squared. So I'm giving you everything here. I'm giving you supply and demand. And the first question, we're going to find both consumer and producer surplus. But the first question is find the equilibrium point, because we're going to have to know that. Sometimes they give it to you here, we're going to have to find it. So find the equilibrium point. What is the equilibrium point? The equilibrium point is the point where supply equals demand. So I don't even have to graph this. This is going to be when supply equals demand. So that's going to be when q squared plus 10q equals 900 minus 20q minus q squared. And let's see, I'll group everything on the left. So add q squared to both sides, we're going to have 2q squared plus 10q plus 20q is plus 30q minus 900 equals 0. And I guess I'm hoping this factors nicely. The only way I'm going to factor this is if I have a 2q plus something times q plus something. And what I need here is two numbers that multiply together to give minus 900. I'm immediately thinking minus 30 and plus 30. And I can see how this is going to work. If I do plus 30 here, that'll give me 60q. Minus 30 will give me minus 30q. 60q minus 30q is 30q, which gives me my middle number. So this factored nicely. This means q is either, well, we'll go 2 steps here. This means 2q minus 30 is equal to 0. That means 2q is positive 30, or q is 15. Or q plus 30 equals 0. So that means q is minus 30. Remember, q is quantity. We're not going to sell minus 30 units of oil. Q has got to be positive, so that's immediately ruled out. And this means my equilibrium demand is q is 15. That's the equilibrium demand. Q naught, equilibrium demand, is 15. So our equilibrium demand is 15. Equilibrium price, the market price, is plug in 15 into either of those functions, because that'll be the price point where they intersect. So plug in 15 into, say, I'll go with this function, it looks easier. 15 squared I think is 225, plus 10 times 15 is 150, 225 plus 150, 375. Okay, so P naught, equilibrium price, 375. Great. Next up, B will be find the consumer surplus. So consumer surplus is going to equal the integral from 0 to the equilibrium demand, 15, of what? Of the demand function minus the price. So demand function, 900 minus 20q minus q squared minus the equilibrium price, minus 375. dq. I should have erased this too. Again, commit these formulas to memory. So consumer surplus is demand minus market price. And I've gone through all this in my notes, so we might skip a few steps here in the interest of time because the numbers aren't the prettiest thing in the world. But what do we have? Let's see. 900 minus 375. I'm just going to erase some stuff on the board because I don't have a whole lot of space to work with. 900 minus 375, that's 525. So we're really just integrating 525 minus 200 minus q squared. So integrate that, we're going to have 525q minus 20q squared over 2. 20q squared over 2 is 10q squared minus 1/3 Q cubed. And we're plugging in 0 and 15. And if you do that, plug in 15, plug that into this expression, subtract off what you get when you plug in 0, which is actually just going to be 0, that part's easy, but I promise you'll get 3,375. No units were given, but I assume this would be in dollars. And so that's how much all these consumers saved by paying the market price versus what they were actually willing to pay. Last but not least, C, find the producer surplus. I'll be looking R there. Producer surplus, so producer surplus, we go to our formulas again. Producer surplus. It's again the integral from 0 to Q naught, the equilibrium demand, 0 to 15. Of what? Of the market price, P naught, 375, minus the demand curve. Wait, no, not minus the demand, minus the supply curve. Minus Q squared plus 10Q dQ. And again, in the interest of space, I'm going to do what I did last time, which is cheat a little bit. I'm just going to do some arithmetic on the board here. We're going to distribute this negative as we go. So that would be minus Q squared minus 10Q. And we integrate this. We have 375Q minus 1/3 Q cubed minus 10Q squared over 2 is 5Q squared. Evaluate that from 0 to 15, so plug in 15, then minus what you get when you plug in 0, and, oops, I made a copying error. This one is 3,375. Actually, this one is really 3,375. The last one, I actually did make a copying error if you want to go back and check. The consumer surplus, if you work that one out, is not 3,375, it is 4,500. Sorry about that. But that's it. So this economic concept of altogether, these ideas of equilibrium price, consumer surplus, producer surplus is known as economic surplus. So you'll see a few more examples like this for homework. A few where maybe they just give you a supply curve and then they tell you the equilibrium demand or something. I think there's one or two where the integrals you might get might be more complicated. Look out for that. Sometimes you have to do substitution, sometimes you have to break integrals apart. So these integrals that you actually compute might not be the easiest things in the world to evaluate, as they sort of were here. They're just polynomials. But all of your techniques that you know for integration you can still use, substitution and so on. So keep an eye out for that. But that's really it. So yeah, thanks a bunch, guys. Take care.